16 times for your success.
So it takes 15 times in the sense you fail 15 times and then you have success on the 16th time. So number of failures, 15, and you succeed on the 16th time. And that would be equal to
0.01927.
So what is the probability that it takes at least 4 tries for Dr. G to get the name right? At least 4 tries would mean 4 or more, but that would imply how many failures? At least 3 failures. Because it is always 1 less. Now, this is a cumulative CDF, do we agree? Not exactly the cumulative, rather it is the complement of the cumulative CDF that we have. So this is 1 minus the probability of x less than or equal to 2. Because the complement of x greater than or equal to 3 is x less than 3, which would simply mean x less than or equal to 2. Last time this was easy because we got that number by plugging in the complement of 0.1092, which is 0.8908 raised 15 multiplied by 0.1092. Yes, 0.8908 is 1 minus 0.1092. You raise it to the power of 15 multiplied by 0.1092. Here I could do the same thing. Probability x less than or equal to 2 would mean 1 minus. If I have to write it as individual probabilities, what would I get?
X equals 2, x equals 1, x equals 0.
Either x is 0, or x is 1, or x is 2. And I can simply sum the probabilities because they are disjoint. If I say that I had no failures and guessed it the very first time, that would be 0, 1 failure, 2 failures, and so forth. So this would become 1 minus 0.8908 raised 0. I'm just plugging in the values of x is equal to 0, 1, and 2 in the PMF of a geometric, which is q raised k multiplied by p. Now, someone gave me this answer last time. Was it you, Benton? Someone used the calculator and gave me this answer, and they said they used Geom PDF. So I just wanted to verify if you plug this in the way you see, do you get 0.0197?
Yes. Did it, but you have to use 16.
Yeah.
So what is the answer to this? .7069. So there is a 70.69% chance that I will get it right in at least 4 tries. Does that make sense? There is a 10% chance that I'll get it right. So if that is the case, what are the chances that it will take at least 4 tries for Dr. G to get the name right? That naturally is 0.7069. So your calculator does it in a different way. Certainly said it has to be 16, right? So you would get this number if x is equal to 16. So that is the second way in which people define a geometric distribution. There are 2 ways. This case is where you look at the number of failures before the first success. Good? So this specific geometric distribution is also called as first success distribution, because we're talking about the number of times it takes to get the first success. However, the calculator doesn't do the first success distribution. It does the other type, but if you do some algebraic manipulation, sure, you could get to this answer easily. The support of this distribution, where does it start? Yes? Good. So we will get to the second geometric type after we do the expectation. But do we follow? So if you're going to use the calculator, we have to make an adjustment. And the adjustment is simply adding or subtracting 1 depending on the case. So I will explain that when we go to the next type of geometric distribution. Now we can move on to expectation of a geometry. What is the definition of expectation? For a discrete PMF. By definition, I mean, what is the formula? So expectation is simply the sum of every outcome multiplied by its probability. If you recall, this is simply, or is very similar to a weighted mean. We are simply weighting each outcome by the probability that it would happen or occur. So here we start at 0 and go all the way up to infinity. Yes? That would give us k multiplied by q raised k multiplied by p. Yes? We know p is a constant, so you can pull that out of the sum. And you will have k multiplied by q raised k. If that k wasn't there, then that sum is easy. Do you agree? Yes. If this k wasn't there, then sum k equals 0 to infinity, q raised k. Q is a probability. It is going to be between 0 and 1. So what type of series would this be? Geometric. And if I sum from 0 to infinity, all I'm trying to find is the sum of a geometric series, which we know, right? Do we? We did this last time. If the general term is A, or if A is the term, then what is the infinite sum of a geometric series?
A over 1 minus 1.
What? No. Not the nth sum, it's not summing up to n terms. I would like to know the infinite sum. 1 over 1 minus that term, so in this case it will be 1 over 1 minus q. But the issue here is about that k, right? So what do we do about that k? Or what should we do? Can I erase this? I'm just going to write q raised k as q multiplied by q raised k minus 1. Now q is a constant also. Do we agree? So I can pull that out. And I will have k multiplied by q raised k minus 1. Still doesn't help. You know, I just went from k, q raised k to this. But there is a reason why I'm doing that. So I know correct. Now I'm going to take the derivative on both sides with respect to q. What is the derivative of q raised k? K multiplied by q raised k minus 1. Well, I don't want to skip a step. So the left-hand side would be k multiplied by q raised k minus 1. What about the derivative on the right-hand side? Negative 1 over 1 minus q squared. Yes? I was about to go. Then times, thank you. Are we done? There is something else that we are missing. So, times the derivative of that, I forgot to change it. So that would result in 1 over 1 minus q squared. Good.
So on the top, it's being multiplied. Wait, what's the -1 be?
So
With the arrow?
this one?
Yeah.
So I'm changeable. I'm taking the derivative of the inside. Right, so if it is just 1 over x, the derivative would be minus 1 over x squared. Right. But if it is 1 over 1 minus x, it is minus 1 over 1 minus x squared multiplied by the derivative of that, which is -1. Chain rule. So, see, do I have something? So I've got this, I've got that. So that sum is equal to that. Do we agree?
Do we have to change the index? Or is it line to 0?
That's fine. We'll keep it at 0. I mean, it's obvious, right? I have to simply start at 1 by substitution, right? So I'm not going to do all that. I'm just going to keep it from 0. So I will just change expectation of x equals p times q multiplied by let's change the index and see. Let's change the index. 1 to infinity k times q raised k minus 1. Right? Good. We have a k equals 0. If I started at 1, this would still be equal to that. Do we agree? These two are one and the same. So PQ, we know that part. One to infinity, yeah. So when k is 0, m would be 1. And this would become q raised m. Yes? Substitution. I didn't want to skip that step.
K is 0.
Come again?
You said when k is 0, m is 1. But you said m equals k minus 1. So if k is 0, m is
M is k minus 1.
So if k is 0.
Okay, when k is 0, I see what you're saying. You have m is equal to 1 would be the first one. So when k is 0, m is -1, so we have to start at 1. So when k is 1, m would be 0. And that would become m plus 1. This is just making it more complicated than what it's supposed to be. Right? I think I've kept it as is.
Well, stopping us from the substitute right now.
Yeah.
Remember the sum is equal to 1 over.
Yeah, that's right, which is why I skipped the step. I could have just substituted 1 over 1 minus q. It's 1, right?
Yeah.
Yeah, so I didn't want to skip the step, that's why I'm doing the substitution. But this and that are one and the same. So skip that step. You can try that at home. That's what I would have. But what is q? Q is 1 minus p. So p times 1 minus p divided by 1 minus p. So I will have p times 1 minus p divided by 1 and minus 1 will get cancelled. Minus times minus p is plus p. And then you're squaring, you'll have p squared. That will get cancelled. So we will end up having 1 minus p over p. So now that we have the expectation to be 1 minus p over p, on average, I'm sort of, easing into the geometric definition. The last two problems I did number of tries and then I reduced by 1, correct? If you go back and look at the previous problem, when we did the first case, what is the probability that it takes 16 tries for me to get the name right? So we did 16 minus 1, 15. Likewise, which would mean 15 failures. What is the probability that it would take me at least 4 tries? So I change it to 3 failures, at least 3. So I'm not putting tries here because we are trying to find the expected number of failures in reality to find or to see when the first success would happen. So that expectation is given by 1 minus p over p. We know what 1 minus p is, which is 0.8908 divided by 0.1092. 8.1575. Note the word failure. I'm not using tries anymore. In the last two cases, when I use the word tries in the question, we reduce by 1 to get the number of failures. So here, when I find the expectation, I'm not using the word tries, I'm rather using failures. Good. So how many failures would I have? 8 failures. So if I go slightly over 8, I'll have a good chance of guessing the name right. Yes? Okay. So for instance, what is the probability that I would get the name right in at most 10 tries? It is going to be close to 90% or so. Good. Okay. Can I erase this? So the geometric P that we started with, your book calls it as the first success distribution. In reality, there are simply 2 conventions of a geometric distribution. It's just a matter of perception on how you see things. So I already gave you a hint as to what we're supposed to do. Let's say X is the first success distribution. In other words, what does X measure? X measures number of failures before first success. That is how we define the problem, right? This is also a geometric, but your book calls it as a first success distribution, but that's okay. I think the author wanted to distinguish between the 2 types of geometric functions. Last time, I called this geometric. It is geometric, but what does it do? The way we defined it, it measures the number of failures before the first success. Now, I am going to define Y as the number of trials required for the first success. Good. Good. With me so far. So now go back and look at the problems, the probability problems that I did. Number of trials. When we wanted to find the number of trials and related it to the number of failures, what did we do? Right before finding the probability. Sydney, you have the answer. You corrected me at the beginning of class. We subtracted by 1, right? So any time we found the number of failures, we knew that, or number of tries, it is always the number of failures plus 1, right? That is the number of trials you would need. So if I have to write probability of Y is equal to K, yes, that would equal to the probability of X plus 1. Yes, so in other words, you have Y to be equal to X plus 1. The number of trials required. That is the number of failures. And what is that? Why do we add that one? That is that one trial where success happens. So if I want to find this would be equal to probability x is equal to k minus 1. Correct? So how would the formula change?
K minus 1.
K equals k minus 1.
K becomes K minus 1.
Well, Nathan, well.
In the formula.
In the formula. So Q, last time it was Q raised K multiplied by P. Here it is Q raised K minus 1 multiplied by P. Good. But what is the support? Okay. Can I start at 0? If you had no trials at all, is it possible to have a failure or a success? No. At minimum, you need one trial. So 1, 2, 3, all the way up to infinity. Does that make sense? Yes? So this is geometric of type 2. Some people call both of them geometric, and as they go along, understand what's happening. You know, that's what we did last 2 problems when I tried to find the number of tries, and then I subtracted 1 to look at the number of failures. So this is how they are related. If you are measuring the number of trials required for one success to happen, then it is geometric of that kind. Q raised K minus 1 times P. The support is K from 1, 2, 3, and so on. If you're measuring the number of failures before the first success, it is geometric with parameter P, but its support is from 0 all the way up to infinity, and instead of K minus 1, you will have K in that formula. Your book tries to distinguish it and call that one as a first success distribution and that one as a geometric distribution. But in reality, both of them are geometric distributions. Does that make sense? Okay. So we can go to previous problems on Dr. J. The first one, we wanted to find probability that x is equal to 15, right? Yes, which would imply x, y is equal to, Sydney, does the calculator do this or the other way around?
16.
It does 16?
Yeah.
And very fast at one.
So, in other words, what is the calculator doing? The calculator is trying to find the number of trials required to have the first success. Yes, but we know y is x plus 1. So this would be equal to probability of x plus 1 equals 16. Which is simply probability of x is equal to 16 minus 1, which is 15. This is what something meant earlier. But what does that mean? That simply means the number of failures prior to first success. Do you agree? Mm-hmm. This and that are one and the same. So last time I used the first success distribution. I used the formula to get the answer, but it required some intuitive thinking. But if you're looking for the number of trials required to have the first success, you can put it in the calculator directly. What was the syntax? Is it John PDF X, P?
Geomet.
Oh, Geomet. Geomet PDF.
Yeah.
Okay.
And then 0.192.
So that would be y, and that is p.
What button is this on?
Huh?
What button is this start?
Second bars. Second bars. Remember where we did binomial PDF and CDF? If you scroll down, you should see Geomet PDF. Or if you scroll up from binomial.
Yeah.
Or if you
it's bigger since like the first one.
Yeah. Are we clear? Do we understand the difference between x and y? Okay. Okay, if y is geometric P, I want you to find expectation of y. The process is exactly similar to what we did earlier. Let's see what you get as an answer. Okay, so the reason why I brought this up is this is a great lead-in into something called the linearity of expectation. But I'll get to that at the end. But if I just have to use the PMF, how would I go about doing this? Expectation of y is sum k equals 1 to infinity. K times q raised k minus 1 times p. Yes? Now, last time we had the sum starting at 0 and everything worked out for us. So I'm going to pull P out for now. And I'm going to make a substitution. I'm going to substitute m is equal to k minus 1. When k is 1, what is m? 0. When k is infinity, what is infinity minus 1? Infinity. So m is equal to k minus 1, so k is n plus 1. Q raised m. Yes? Which would equal to p, sum m equals 0 to infinity m times q raised m, plus sum m equals 0 to infinity q raised m. Good. Let's review. M raise Q raise M plus I'm distributing that P, so P. Sure, I could take the algebraic approach and come to a conclusion, but I'm going to think like a statistician. So now, why is it so important to think this way? You know, Dennis asked about chi-square distribution and T distribution and all that. So they're all related to a gamma distribution. So if you understand how to represent one distribution in terms of another, your calculations will be very easy. So the second term, I'm going to write it as PQ raised M. Mind you, you could do this using the algebraic way, calculus way, geometric theories, whatnot. But I'm going to think like a statistician and do this. Why? What does that say?
One is the distribution of X.
Very good. So this is simply the PMF of a first success distribution with probability P. Now, what would happen if you sum over all possible values of a PMF? You get 1. So I get 1, but still though, if I want to use the trick that I used last time, I need a -1. So what should I do?
Can we just say that's E of X? Like E of X plus 1.
Oh, you just put the P back in and call it expectation of X. Yeah, sure, that's fine. That's actually a much more nifty approach. But ignore the nifty approach. So if you had to manipulate this, how would you get a -1 there? Basic algebra people. Plus or minus. Oh, okay. +1 minus 1. It's the same as multiplying and dividing by q. So if you recognize that that part is simply the expectation of X. If you go back and look at the formula of expectation of X, it'll match up to that. So that is 1 minus P over P. Correct. +1. Common denominator and add, what is the common denominator? P. We have a common denominator of P, add the numerators, 1 minus P plus P is 1. Good.
I thought of an interesting way of doing it from the start. So basically, when you have P times the infinite sum for K equals 1, the K times Q to the K minus 1, you're essentially, if you were to write out like almost padding out like 1 plus 2Q plus 3Q squared, etc. So then you can break that up into 1 plus Q squared plus Q squared plus Q cubed, etc., etc. So you actually have like an infinite sum of infinite sums. So then
yes, that is correct.
So then you can establish that as being 1 over 1 minus q plus q plus over 1 minus q, etc. When you get your infinite sums. And that's just another infinite sum. So you get 1 over 1 minus q all over 1 minus q, which is 1 over p squared. And you have the p of star 1 over p squared times p.
That is correct. There's nothing wrong with this. But guess what? We like to eat our sandwich this way. Not that way.
Well, this way didn't take up all the whiteboard.
There is nothing wrong, but it is a great approach. I agree with Dennis. That is a nice way of doing it. It's much more work than this. You say tomato, I say tomato. So going back to, well, before we get back to the Dr. G problem, expectation of y ended up being expectation of x plus 1. Do you agree? What is y from the get-go? X plus 1. So that is what we call the linearity of expectation. So if you know expectation of y is expectation of x plus 1, which would mean expectation of x plus the expectation of 1. Expectation of a constant is the constant itself because expectation applies only for random variables. So plus 1. We know the expectation of x. So we'll just keep it as is. So let's go back to the previous problem. Expectation of x was 8 point something, was it not? 05 or 15? 15. Well, naturally, expectation of y would then be equal to 8.15 plus 1, which is 9.15. There, 8 failures. Here, 9 tries. But they are equivalent. Do you agree? Yes. If you recall correctly, when I wrote that question here, initially I wrote the expectation of the number of tries, and I quickly erased tries and changed it to failures because of this. Sure, in terms of PMF, we can manipulate and get a different answer. But when you come to a conclusion using averages, you've got to be practical. You've got to know the difference. So when we found expectation of x, we had 8 failures, which simply means you must have 9 tries. Does that make sense? Okay. I'll write the general property of linearity of expectation. In general, you have some value, AI are real numbers. You multiply that by xi. You can pull the constant out and distribute the expectation. You may say, well, that's trivial. Why do we need this? Well, we need this when we go to transformations, sums of random variables, and such. Good? Are we clear? So when you find sums of random variables, it might be difficult to find the distribution or the PMF, but it might be easier to find the expectation. So that's good enough for us to come to a conclusion. Does that make sense? you know, if you had to convey information to people. So this helps. We will use this later when we go to memory generating functions also. Good. Any questions?